Okay, I think we'll get started. We're a little bit late. I think the keynote was a little bit late too, so we'll try to finish this so you get in time for the next presentation. So welcome to this talk about design. We call it Xtext on the cutting edge, and I think you'll understand why we call it that a bit later. My name is Martin. I work for a company called Sandvik Coromant. It's based in Sweden. We got representation all over the world, but the headquarters is in Sweden. I've been working with knowledge-based mechanical engineering for like 10 years or so. And with me I have Esa, who is working as a consultant in his own firm called E-Rules. And he's been into knowledge-based mechanical engineering for 20 or 25 years or so. So this design is a sub-project of a bigger initiative called YAP. So that's why the logo looks like it's supposed to look like a Y anyway. So Sandvik Coromant is a company selling tools for the manufacturing industry. So you usually find our customers in the car industry, energy, or aerospace. So what's our problem domain? I'm going to try to illustrate this through this tool, which is a Core Mill 390. The application area of this tool is surface milling. So what you want to do with this is create planar surfaces and square corners. So this is what we call a tool family. And at Coromant we have roughly 100 families covering different application areas. And all our tools are designed and maintained in a 3D modeling CAD system. And along with the tool comes metadata such as drawing, simulation models, functional parameters like ISO, standard definitions. This Core Mill 390 comes in 150 different variants off the shelf. So this means that you can find 150 different variants from our main catalogs, basically. And it's usually delivered within 24 hours. So on this picture here, you see a few examples of these 150 variants. And even though they kind of look different, they all belong to the same family and they are all designed to do the same application, that is face milling. And from these 150 variants, you can choose a diameter that is between 12 to 200 millimeters and a length that is between 20 to 120 millimeters. There are a number of inserts that is from 1 to 14, and the insert is this super hard material that is doing the actual cutting. And the inserts are to us what razor blades are to Gillette. It's the sort of what you sell all over and over again. The inserts comes in 3 different sizes in this family, and you also have 5 different coupling types coming in 45 different sizes. And couplings are actually the interface or that part that is you put into the machine. So we found that developing and maintaining so many instances is very time-consuming and labor-demanding. So is there a more efficient way to tackle that problem? So looking at these 150 tools in this Core Mill family, there are a lot of similarities. As I said, there's a front part that is used for the cutting, there's a back part that is used for mounting in the machine, and we also have a finite number of inserts. So what we do is a logical separation of this tool into module types or classes. Each module is independent of each other, and that makes them replaceable and reusable. So when we've done this classification, we can then populate each class or module type group with instances of that specific class. So using just a few instances of these module types, we can actually make these 150 variants of these tools. What we also gain by doing this is that we can actually make tailor-made tools for customers that are not within our main catalog or that's presented as an off-the-shelf product. So modularizing is just half the way to the solution of our problem. We also want to automate the assembly of these modules through a program. So this is where Xtext comes into play. So we're going to show you a demonstration of what our system and what our DSL looks like. And what I'm going to do is this logotype that we have, we're going to create this in this CAD modeling. So we generate this logotype as well. Not quite as fancy as this one because we are not doing it in a photographic style. But what you can see basically is that this logotype consists of a sphere and a letter Y that is sort of cut out of it. So I'm going to give the microphone to DESAGN and he can talk a little bit more.
Give me the screen first. Okay. So, can you hear me? Yes. Great. Okay, we're going to give you a very quick tour of the language design and also some of the tooling behind it. As you understand, this DSL is based on Xtext framework, Eclipse. But anyway, we should show this JAP logo demo. Hopefully you can see or read the text here. Here we have one of the concepts in our language is called a model. It's not the EMF model, which maybe Eclipse people associate with models. It's a CAD model, a 3D model we are talking about. And I'm not going to go into detail what's happening here, but basically in a model you do CAD work. So in this model we bring in some spheres, the letter Y, and do some Boolean operation, uniting and subtracting solid bodies. That's what you do in a CAD system. So I just start by running the program, so you see some action. One more time. So, it's quite cool, we can make our own logo. It's like a meta logo, our program is like a meta logo. So we have it here in the CAD system. A few words about the runtime. We are using, we're using the Eclipse launching framework. We are running in OSGI containers, we're using Equinox. This DSL is actually compiled to Java. So if I open Java file, so here is actually the Java representation of this DSL file. And as soon as you change the DSL file, a new Java file will be compiled. I mean, this is part of the Xtext framework. So we are not running the DSL itself, but we are running compiled Java code. Okay, I have two other demos I want to show you. Just close all the stuff here. Here we have another model. Here we're going to do a block with a hole. I show you some of the tooling stuff. We have hovers. So this is basically what we're going to do now, to make a block with a hole. It's very, very simple. So we have a block and a cylinder, and we subtract the cylinder from the block. Some of the features of the tooling. Here you see we have an outline. I mean, that is something you are familiar with on JDT. You get this more or less for free from Xtext. We have syntax coloring and that kind of stuff. But let's look into details how this is implemented. And as Martin explained to you, this modularization of the tool itself, the cutting tool, these modules are implemented in parts. And they're not like E4 parts or like any of this user interface stuff. Parts are parts in a CAD system. So I will open the parts so you see what they are. So here is the block geometry. Here's the cylinder geometry. And these geometries, they are parametric, as they're called. So they are controlled by expressions in the CAD system. So for example, I can change the diameter from 20 to 50, for example. That is like the basics of this. So modeling in the way we are doing is like modeling with Lego pieces, except that we have rubber Lego, so we can resize our Lego pieces. So these are like the models. For each of these CAD parts, we have a corresponding DSL construct. So the cylinder is represented by what we call a part. And this file could actually be automatically generated from the CAD part, even though at this moment we write them by hand, but they could be auto-generated. Basically, it's a declarative description of the contents of the CAD geometry. So here we have like the file name of the part file, cylinder.prt. The purple stuff here, diameter and height, they correspond to those expressions that I changed right now. The blue ones here, like XY plane, these are like hidden geometry that you didn't see. They're like datum planes representing a coordinate system, because this geometry has to be positioned somewhere, so you need to have some kind of positioning references, and we usually use coordinate systems for that one, and a coordinate system represented as three planes. So we have those 3 planes represented here as YZ plane, XZ plane, and XY plane. And then we have some helper stuff like the CSys, we don't have to go into detail. And we have the cylinder here, which actually is the cylinder body. Basically, a part file consists of features, and these are not the EMF features either. We have some kind of named conflict with EMF all the time here. But here we are using the cylinder is a body, a solid body. That's what we're modeling with. And you can see all those methods here, like find body. They are actually Java methods that gets inherited. So they are implemented in Java. So the generated Java code actually, so to say, inherits from the framework that does the heavy lifting, so to say, in the system. So we have for every part, we have a part file in the CAD system, we have a DSL part, so we have one for the block as well. And we also have a third part called the assembly part, which basically is an empty part where we assemble the other parts in two. So I don't have to show you that one. Then we have rules. And rules are described in what we call rule sets. In rule sets, you describe dimensioning rules for the modules. So to say, how big should we make in this case, the block. So we have rules for length, width, and height of the block, because that's the controlling expressions for the block. And we have also rules to select the CAD geometry. So here we select the block part, that is the representation of the CAD model. This is a very simple case where we just have one block to select from. But here there could be rules to select among several different kinds of blocks, for instance. These rules are implemented using the Xbase expression language that you get from Xtext. So everything to the right side of the equal sign are Xbase expressions. You have like height divided by 2, which are arithmetic expressions. You have if then else, while loops, for loops, I mean everything you are used to from Java. And what is not shown here, we have also closures.